Okay, so lesson 8B. So rational functions and graphs. And so we'll start out here. We're doing the same thing we were doing in 8A. So we're going to just graph this. We're going to go through all of our steps. So remember, step 1 was to simplify the rational function. Sorry about that. So first thing we need to do then is we're going to factor. So we're going to use our X box. So we're looking for two things that multiply to 4 that are going to combine to that -5. So -4, -1. And so we get 2x minus 4, 2x minus 1, which gives us x minus 2 times 2x minus 1 over, and the denominator we're doing x box as well. It gives us with x minus 2 and x plus 1. So we can see our x minus 2's will cancel. So we're left with 2x minus 1 over x plus 1. All right, step 2 is talking about the domain. And so our domain is where our denominator cannot equal 0. So we know it's where x minus 2 cannot equal 0 and x plus 1 cannot equal 0. So x cannot equal 2, x cannot equal -1. So we know our domains from -infinity to -1, -1 to 2, and 2 to infinity. All right, then we're going to go find those zeros of the numerator and the denominator. So zeros of the numerator are x minus 2 equals 0 and 2x minus 1 equals 0. Solve them both for x, so add 2. And this side we're going to add the 1 and then divide by 2. And the denominator. So that's where the x minus 2 equals 0, x plus 1 equals 0. So we get x equals 2 and x equals -1. All right, then step 3. We should do the x-intercept, which remember is what's unique to the numerator. And so we can see unique to the numerator is the 1/2. So 1/2, 0. And the y-intercept, that's where we're going to plug in 0 for x. So using my simplified version of my equation. So -1 over 1, which is -1. So then step 4 is the vertical asymptote in the wholes. So vertical asymptote is what's unique to the denominator, which is the -1. So x equals -1. And our wholes, remember what's common in the numerator and the denominator. So that's the 2. So we know it's 2 comma, and we're going to plug the 2 into our simplified equation to find its y value. So 4 minus 1 is 3 over 3, which is 1. All right. And then I'm going to erase some of what I have up here to make some room. So let me go back real quick. So this was, my simplified was 2x minus 1 over x plus 1. So don't forget that. All right, so step 5 is my horizontal asymptote. So remember, so where's the highest degree? Top, bottom, or both? It's both here, so it's going to be the 2 over 1, so that y equals 2. And then we need to see, is it going to cross? So I'm going to take my simplified version of my equation here, set it equal to the horizontal asymptote, and try to solve it. So I'm going to multiply both sides by x plus 1. So we get 2x minus 1 equals 2x plus 2. And my 2x's are going to cancel, so there is no x to solve for. So no, it will not cross. And then we got to check for a slant or an oblique asymptote. And since we have a horizontal, there's not going to be one. Then 6 wants us to check for symmetry. So this is where we're going to plug in negative x into our function. So it gives me negative 2x minus 1 over negative x plus 1. It's not exactly the same, so it's not even or symmetric to the y-axis. All the signs didn't change. It's not symmetric or odd, so there is no symmetry. All right. And then step 7 is where we do our interval. And so I'm going to draw myself a number line here. Put my infinities. I'm going to go ahead and graph everything I've got. I don't graph 1 or 2. 3 is my x-intercept at 1/2. My y-intercept at negative 1. Vertical asymptote at negative 1. A hole at 2, 1. Horizontal asymptote at 2. And no slant asymptote. All right, so looking across my x-axis there, I can see I have a vertical asymptote at negative 1. And I have an x-intercept at 1/2. And so I'm going to pick some values in between those intervals. So I'm going to pick like negative 2, 0, and 1. So I'm going to plug the negative 2 in. I'm going to plug in negative 2. I get 5, which is positive, which tells me it's going to be above the x-axis. When I plug in 0, I get negative 1, which is negative, which tells me then it's going to be below the x-axis. And when I plug in the 1, I'm going to get 1/2, which is positive, which is above. And again, I expected them to alternate, and it does. So between negative infinity and negative 1, this tells us it's going to be above the x-axis, which I can't be here because then I'd have to go below, so we're not going to draw there. So it means it's all above, which is up here. Then I can see from negative 1 to 1/2, we're going to be below the x-axis. Now that 1/2 is an x-intercept, so come out of it, go towards the negative 1. Because it's below, we're going to go down. Make sure you go through that point that's there. And between 1/2 and infinity, we can see we're going to go above the x-axis. So the 1/2 is an x-intercept, so come out of the 1/2, go towards infinity, go up. Make sure you jump over that hole, and you're shaped by that asymptote. All right. So constructing a function from its graph. So let's look at this. We can pull some things off of this graph that are going to help us come up with our equation. So I can see that we have an x-intercept at x equals 0. Remember, your x-intercepts are unique to the numerator. So this is going to be the numerator only. And that factor would be x plus 0, or we could just say it's going to be x. Okay, because x plus 0 is just x. I can see that we have vertical asymptotes at x equals negative 2 and x equals positive 2. Remember, vertical asymptotes are in the denominator only, which means their factors are going to be x plus 2 for the first one and then x minus 2 for the second one. Also, looking at the end behavior, we can see that there's a horizontal asymptote at y equals 0. So remember, 0 means that the larger degree is in the denominator. And we can also tell on this one that this one is symmetric to the origin. All right, and so let's talk about that. So you see how like over here we have this piece, and then what kind of our quadrant 4, we have like a reflection across the origin there of it. And then the same idea here, we've got this piece of our graph, and across the origin there we got the other piece. It's almost like a mirror image. So remember though, to be symmetric to the origin, it has to be symmetric across the x and the y axis. So let me back up here. If I take this first piece right here and I reflect it across the x, and then I reflect it across the y, it will lie on top of itself. Okay, and the same thing if I take this piece. If I take that piece and I reflect it across the x, it's right there, and then when I reflect across the y, it lies on top of itself. So therefore, we can see that this is symmetric to the origin. All right, so let's see what we've got. So we're just going to come up with some rational function here. So we know, according to this, in our numerator, we're going to have an x. In our denominator, we're going to have that x plus 2, x minus 2. And so I'm just going to pick some x value, and I'm going to choose this -3. I know that if I plug in -3, then that my function should be positive. So this is just a check if my signs are good. So when I plug this in, I get -3 over -3 plus 2, -3 minus 2. Whoops. So it's -3 over -1 times -5. So this is -3 over 5. That's negative, but I needed positive. So that tells me then that I need to make one of these negative. So I'm going to put a negative on the top. So now I'm looking at r of x would equal -x over x plus 2, x minus 2. Also, when we look at this though, it looks like this point here is approximately -3, 1, okay? Even if I've changed this, so what I've got written right now will make that a positive 3/5, it's still not quite big enough. So I need to make it a little bit bigger. So let's try multiplying by a 2 as well. And so let's try that. So now let's try the -3. Oops. I looked at the wrong equation. So -2 times -3 on top over -3 plus 2 times -3 minus 2. So it's going to give me 6 over, this doesn't change, so this is still going to give me a positive 5. 6/5 is a little bit more than 1. That's really close. So this equation will work. Okay? If it had been too big, then I would need to pick a little bit smaller than 2. Okay? You may have to adjust your numbers a little bit there. All right. And then we can also check it with the positive 3 as well. So if I plug in positive 3, I expect it to be somewhere right in here, which if I look at the positive 3, it does look like it's a little bit below it. If I plug in r of 3, I'm going to end up getting just a little bit smaller than -1 as well. Let's try that. -6 over 5 times 1. So -6/5, which is just a little bit more. It's like -1.2. So that's close enough. So I think our equation is pretty good. All right, so you may have to play with the numbers a little bit to figure out which numbers you need to use. All right, let's switch gears. Let's talk about the binomial theorem. So the binomial theorem, it says, when writing out the binomial expression a plus b to the n, where n is a positive integer, the pattern known as Pascal's triangle appears, as well as other interesting facts to be discovered. In order to expand the binomial expression, we need to know how to find the binomial coefficient. And so the expression n above r is called a binomial coefficient, and is defined by n above r is equal to n factorial over r factorial times n minus r factorial for non-negative integers n and r with n greater than or equal to r. The symbol NCR is often used to replace or used in the place of N above R notation. All right, but what's a factorial? This just means that whatever number's in front of that exclamation point, the factorial, you're going to multiply that number times every excuse me, whole number below it all the way down to 1. So, for example, if we have 3 factorial, this just means 3 times 2 times 1. If I have 5 factorial, this means 5 times 4 times 3 times 2 times 1. Now, if you have 1 factorial, that's just equal to 1. And if you have 0 factorial, that's also just equal to 1. So let's try this. So we have 6 above 2. So according to our formula, this means we're going to take 6 factorial divided by 2 factorial times the difference in those, so 6 minus 2, which would be 4 factorial. So we're going to have 6 times 5 times 4 times 3 times 2 times 1 over our 2 factorial is 2 times 1 times our 4 factorial, which is 4 times 3 times 2 times 1. All right, now notice I have 4, 3, 2, and 1 on top and bottom here, so I can cancel those out. And then we end up with 30 over 2, which is 15. Now, notice the ones that we canceled out were the 4 factorial there. So if you notice that on top or bottom you have factorials and one of them is smaller than the other, you can bring it down to just that factorial. So like this 6, I could have written it as 6 times 5 times 4 factorial over, and on bottom I would have worked out the 2 times 1 times the 4 factorial, and then we could just cancel the 4 factorial that way. So if you notice, you're going to have the same on top and bottom. You can stop there so that you can cancel. All right, so let's look at B. So we have 9 over 4. So we're going to do 9 factorial over the 4 factorial and then the difference between them. So 9 minus 4 is 5 factorial. So I'm going to take this 9 factorial. It's 9 times 8 times 7 times 6 times 5 factorial, because it's the biggest one that's on bottom, over, on bottom I got 4 times 3 times 2 times 1 times 5 factorial. And so I know my 5 factorials will cancel. And then I have some other things here that will cancel as well. So like I know 4 times 2 is 8. And then I could reduce the 9 and the 3 or the 6 and the 3, whichever, doesn't matter. But if I just type in the top, so I have 9 times 7 times 6. Over on bottom I have 3 times 1. I end up with 126. And then our last one, 3 over 3. So it's going to be 3 factorial over 3 factorial, 0 factorial. So we've got 3 factorial over 3 factorial. Remember I told you just a minute ago, 0 factorial is equal to 1. So 3 over 3 factorial cancels. So you just get 1 over 1, which is 1. All right, and this is the same as it's another way of doing Pascal's triangle. So Pascal's triangle always starts out with a 1 at the very top, and then you have the ones here kind of surround it, and then you're going to put a 1 on the outside, add these two together to get the 2, and a 1 on the outside. Same thing, 1 on the outside, 1 plus 2 is 3, 2 plus 1 is 3, and a 1 on the outside. So if we kept going, we'd put a 1 on the outside, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and a 1 on the outside. And these will tell you the coefficients of the variables for inside. So like here, if it's x plus y to the 0, we know it's just equal to 1. If it's x plus y to the first, then these are my coefficients. We're going to have x to the first, y to the 0, plus x to the 0, y to the first, and those are the coefficients that go in front of it. So you end up with 1x plus 1y. Same thing when we do the next one. So when I do x plus y squared, you're going to get 1x. Let me actually erase some of this a little bit here. Leave that one. So we would get 1x squared y to the 0 plus 2xy plus, I didn't have a 2, plus 1y squared. This should have a 2, right? Oops. Well, sorry, I've hit something. Here we go. It should have a 2 right there. I don't know why it doesn't. All right, and then we can see it in the third one. We know our coefficients are going to be 1, 3, 3, 1. We always start with our first variable with the largest exponent. So we're going to start with our x cubed. And then each term we have x cubed, then it's going to have x squared, then it's going to have x, and then it's going to have no x. And we do the opposite with the other variable, okay? So it's going to start out with none of them. So we're going to start out with no y, so y to the 0, y to the first, y to the second, and y to the third. All right, and then we just put these numbers in front of them for their coefficients. So just for grins and giggles and extra practice here, what if I had x plus y to the fourth? Well, we know, I'm just going to leave so we'll come back and put our coefficient. It's going to be x to the fourth, y to the 0, so don't put it, plus coefficient x to the third, y to the first, plus coefficient x squared, y squared, plus coefficient x to the first, y to the third, plus coefficient no x, y to the fourth. And then my coefficients are the numbers that we wrote right here. So it's going to be a 1, 4, 6, 4, and 1. And so that would be our equation right there, x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth would be our answer. Okay, it's just another way to keep us from having to multiply them all out. All right, so knowing that, let's look at example 7. It wants us to expand x minus 2 raised to the third. So this is going to be our row 0. Okay, it's if it's raised to the 0, raised to the first, raised to the second, raised to the third. So we know these are going to be our coefficients, okay? So I'm going to go through here, and I'm not going to worry about my coefficients at first. So I'm going to have my coefficient, and I know it's going to be x to the third, negative 2 to the 0, plus my coefficient. The x is going to go down by 1, so x squared, and the negative 2 is going to go up by 1, so negative 2 to the first, plus my coefficient. X is going to go down by 1, so x to the first. The negative 2 is going to go up by 1, so squared. Plus, dang, I wish I hadn't, sorry, I should have never written it so close. So plus my coefficient, and my x is going to go down to 0, so there's no x. And my negative 2 is going to go all the way up to 3, which is where I stop at because we're at the third. All right, now my coefficients, because I'm from row 3 there, is going to be 1, 3, 3, 1. And then I can just work this out. So we have 1 x cubed, and 2 to the 0 is just 1, plus, here we have, well, let me write that out actually. Let me do this. So we have 1 times x cubed times 2, negative 2 to the 0 is 1, plus we have 3 x squared, negative 2 to the first is negative 2, plus 3 x, and negative 2 squared is 4, plus 1, and negative 2 cubed is negative 8. And then here we just get x cubed minus 6x squared plus 12x minus 8. And there's our answer.